Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the omniscient machine. In this page, we will cover the fundamental limitations of modern systems that appear to know everything. Imagine a machine that has read every single book ever written and scanned every photograph in existence. It has mastered 100 different languages and can speak with the eloquence of a poet. Billions of people around the globe look at this and call it truly intelligent. However, if you ask this machine why a dropped glass shatters, a profound and deep limitation is immediately revealed to us. This machine does not actually simulate the laws of physics or understand the structural integrity of glass. Instead, it only produces the most statistically probable sequence of words based on its massive training set. It has never actually dropped a glass or felt the gravity of our world. It has only ever seen data, never experienced the reality that the data represents. This gap between seeing and being is the core of our exploration today. In this section, we talk about the smartest parrot in history. In 1907, a horse named Clever Hans became world famous for doing math. If asked 12 minus 5, he tapped his hoof 7 times. People were amazed and thought the horse possessed human-like reasoning. But Hans was not actually doing math in his head. He was reading unconscious micro-expressions in humans to know exactly when to stop tapping his hoof. Modern artificial intelligence is Hans at a civilizational scale. It is an astonishing pattern recognition engine that picks up on subtle cues in data. However, fluency is not the same as understanding. Just as Hans was not a mathematician, a language model is not necessarily a thinker. It recognizes patterns without knowing the underlying logic of the operations it performs. We must be careful not to anthropomorphize these systems or assume they have internal models of reality just because they can mimic human outputs so convincingly. Understanding the Hans effect helps us see the current state of artificial intelligence more clearly and objectively. This brings us to the concept of the hallucination of intelligence. Modern artificial intelligence notices what appears alongside what in its massive training data. It knows the word shatter statistically follows the phrase dropped glass with high frequency, but it has no mechanistic theory of gravity, force, or fragility. It simply matches your question to existing patterns in its training data without any internal logic. This is the difference between a tool that predicts the world and a mind that truly comprehends it. When the system hallucinates, it is not lying. It is simply following a statistical path that does not lead to a factual destination. Because there is no underlying model of physical reality, the system can confidently state things that are physically impossible. True comprehension requires more than just knowing which words belong together. It requires an internal representation of the laws that govern the universe. Without that representation, the intelligence we see is often just a high-fidelity reflection of the data provided rather than a separate thinking entity with its own grasp of truth. Next, we examine the trap of spurious correlation. If you train an artificial intelligence on millions of photos, it learns statistical shortcuts to identify objects. For instance, it might think the word boat simply means blue pixels of water. When shown a boat dry docked in a warehouse, the artificial intelligence often hesitates or fails completely. It never learned what a boat actually is as a physical object. It only learned the environment that usually surrounds it. This is a major issue because the system relies on context rather than core features. If the context changes, the system breaks. This highlights the fragility of pattern matching. A human knows a boat is still a boat whether it is in the ocean, on a trailer, or inside a building. The machine lacks this conceptual permanence because it lacks a causal model of what makes a boat a boat. This reliance on shortcuts can lead to dangerous errors in fields like medicine or self-driving cars, where the environment is constantly changing and novel situations are common. We need systems that understand the essence of objects. Consider the classic example of ice cream and shark attacks. Ice cream sales and shark attacks both peak during the summer months. An artificial intelligence trained purely on this correlation might conclude that eating ice cream actually causes shark attacks. It completely misses the hidden confounder variable, which is the summer heat. The heat causes both an increase in ice cream consumption and an increase in people swimming in the ocean. An artificial intelligence that cannot represent a confounder is confident, fluent, and dangerously wrong. This illustrates the danger of confusing correlation with causation. In many real-world scenarios, the relationships between variables are complex and layered. If we rely on systems that only see surface-level associations, we risk making decisions that are based on false logic. Understanding causality is essential for any system that is meant to operate in the real world, where intervening in one area might have unexpected consequences in another. We must teach machines to look for the hidden drivers behind the data they process every day. Now let's talk about the geometric wall of transformers. Adding 1 trillion parameters to a large language model does not solve the correlation trap we just discussed. Transformers are fundamentally associative engines. They fit a high-dimensional surface to training data by calculating what tends to follow what in a sequence. But they are mathematically blind to cause and effect. The geometry of their learned representation has no direction because it only knows proximity within a vector space. Imagine a library where books about fire are near books about smoke. The system knows they are related, but it does not know that fire causes smoke. This lack of directionality is a fundamental hurdle. No matter how much data we feed into these architectures, they remain stuck in a world of associations. To move beyond this, we need a different kind of mathematical framework that can account for the flow of influence. Scaling up existing models might make them more fluent, but it will not automatically grant them the ability to understand the causal structure of the universe, which is inherently directional. To address these issues, we look to Turing Award laureate Judea Pearl and his ladder of causation. He proved that reasoning requires 3 distinct levels of cognitive machinery. The first level is association, or seeing, which asks what goes with what. This is where virtually all modern artificial intelligence is permanently confined. The second level is intervention, or doing, which asks what happens if I change a specific variable. The third and highest level is counterfactuals, or imagining, which asks what would have happened if I had not taken a certain action. Most current systems are brilliant at level 1, but are completely incapable of moving to level 2 or 3. Without the ability to intervene and imagine, a machine cannot truly reason about the world. It can only report on what it has already seen in the past. Moving up the ladder is the next great challenge for the field of computer science. It requires moving from passive observation to active participation and abstract thought about possibilities that have never occurred. Let's explore the missing rungs of intelligence in more detail. To cross the boundary from prediction to true comprehension, an artificial intelligence must learn to intervene and imagine. Level 2 involves the realm of agency and randomized controlled trials. This means forcing a change in the environment to see the resulting effect. Level 3 is the summit of human consciousness. It involves reasoning about alternate realities and scientific hypotheses. Humans do this naturally. We wonder what would have happened if we had taken a different path, or if a different law of physics applied. This ability to simulate non-existent scenarios is what allows for true creativity and scientific progress. Current models are backward-looking mirrors of their training data. They cannot imagine a world that is fundamentally different from the one described in their texts. To reach human-level intelligence, machines need to be able to build internal simulations where they can test ideas without needing to see them in the data first. This transition is essential for creating systems that can solve entirely new problems. One way to achieve this is by drawing arrows through reality using directed acyclic graphs. We cannot extract causation from correlation alone. We must hard-code the laws of physical reality into the artificial intelligence or allow it to discover them through specific structures. This requires using graphs where arrows represent strict and one-way physical or logical flows. By doing this, we map the causal structure of reality. These graphs act as a skeleton for the machine's thinking process. Instead of just seeing that 2 things happen together, the machine sees that one thing leads to another. This provides the directionality that is missing from standard transformer models. It allows the system to understand that flipping a switch causes the light to turn on, rather than just knowing that switches and lights are often mentioned in the same paragraph. Mapping these relationships is a difficult task that requires expert knowledge and a clear understanding of the domain. But it is a necessary step for building robust and reliable causal systems. The mathematics of intervention becomes possible once we have a causal graph. We can use what is called the due calculus. This is the mathematical difference between observing a variable, which is passive, and forcing a variable, which is active. For example, observing that people carry umbrellas when it rains is different from forcing everyone to carry an umbrella to see if it causes rain. This breakthrough allows us to mathematically strip away confounders and calculate isolated causal effects from purely observational data. It is like having a magic wand that can clear the fog of correlation to reveal the truth beneath. This is incredibly powerful for fields like medicine and social science, where we cannot always perform experiments. By using the due calculus, we can make better predictions about the results of our actions. It transforms the artificial intelligence from a passive observer into an active strategist that understands the levers of the world. This mathematical foundation is what enables a machine to move up the ladder of causation toward true reasoning. A promising path forward is neurosymbolic artificial intelligence and structural models. The path to causal intelligence requires marrying two distinct traditions. First, we have deep learning, which provides the rapid and intuitive pattern recognition of neural networks. Second, we have symbolic artificial intelligence, which provides a rigid and logical causal layer built on structural models. In this hybrid system, the neural network proposes patterns, and the symbolic layer verifies them against the laws of physics and logic. This is similar to how the human brain works with an intuitive fast system and a logical slow system. By combining these two approaches, we get the best of both worlds. We get the flexibility and power of modern models, along with the reliability and explainability of classical logic. The symbolic layer acts as a guardrail that prevents the system from making nonsensical or impossible claims. It ensures that the outputs of the machine are grounded in a consistent and logical framework that matches our understanding of the physical universe. We can also help machines by letting them learn by breaking things. Currently, artificial intelligence learns passively like a sponge. Human infants, however, learn by systematically exploring causal structures through dropping and breaking things. They are natural scientists who perform thousands of little experiments every day. Through interventionist training in simulated physics engines, artificial intelligence agents can play in world models. By changing variables and observing the outcomes, they build a rich and internal simulation of reality. Instead of just reading about gravity, the machine can experience it in a virtual world where it can push objects off tables and see them fall. This active learning process creates a much deeper and more resilient form of knowledge. It allows the machine to understand the why behind the what. When a machine learns through action, it develops a sense of agency and a better grasp of how the world works. This move toward embodied and active learning is a key part of the journey toward artificial general intelligence. We must also consider the danger of false causality. When an artificial intelligence hallucinates text, it is usually easy to correct. However, when an artificial intelligence confidently hallucinates a false causal link, the results can be catastrophic. If a super smart system incorrectly determines that a harmless variable causes a market collapse and we act on those delusions, the real-world impact could be devastating. This could affect everything from economics to global geopolitics. A system that thinks it understands the levers of power, but is actually just chasing a ghost in the data, is a liability. This is why causality is not just an academic concern, but a safety concern. We need to be able to audit the causal logic of our systems to ensure they are not making critical decisions based on false premises. Ensuring that our machines have a correct and verified model of cause and effect is one of the most important tasks for researchers and policymakers in the coming years. This brings us to the comparison of the mirror versus the engine. A mirror perfectly reflects the world, but it understands nothing of what it shows. Current artificial intelligence is essentially a mirror of human knowledge. It is a passive conduit for statistical patterns that we have already produced. In contrast, causal artificial intelligence is like an engine. It does not just reflect the past, it understands the mechanics of reality well enough to actively drive us into the future. An engine has moving parts that interact in specific ways to produce a result. By understanding these interactions, we can build better and more efficient machines. Moving from a mirror to an engine represents a fundamental shift in how we think about technology. We are moving from tools that show us what we already know to tools that can help us discover what we do not yet understand. This transition will redefine the relationship between humans and machines, turning them into partners in the quest for knowledge and progress. Finally, we reach the epistemological leap. The final boundary of artificial general intelligence is moving from a tool that predicts text to an instrument of scientific discovery. To genuinely participate in the human project of understanding the universe, machines must learn to ask the most profound question of all, which is why. This question is the driver of all human curiosity and the foundation of the scientific method. When a machine can ask why, and then set out to find the answer through reasoning and intervention, it will have reached a new level of existence. We are standing on the brink of this transformation. By integrating causality into the heart of our systems, we are giving them the keys to unlock the mysteries of the world. This journey is not just about making smarter computers. It is about expanding the horizons of what is possible for our species. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.